I'm G. Mark Hardy, and I'm here to introduce our next speaker, Tess Schrodinger, who's here to talk to you. Yeah, come on! And she's going to talk to you. Wait, you remember my talk years ago about turning 50? Well, wait a minute. There we go. Now I can read my notes. It's terrible, but they say, I guess, what's your memory is the second thing to go. I forget what the first is. Anyway, she's a security engineer with Digital Cloak. She's going to be talking about quantum computing 101. Thank you very much. I'm glad somebody can read binary. If you couldn't do that, shame on you. She's been doing security for about 20 years or so and didn't look it, so I thought it was pretty good. But she said only in IT for 3 years, so that's good. And I asked her a little bit about pets, you know, with Schrodinger and Schrodinger's cat and things like that. And she's not sure if she has a cat or not, but I said it doesn't matter. They don't come if you call them anyway. But she does have a dog named Sushi, so you can try to hack her account as Sushi123 bang. Anyway, she's going to talk to you about some really cool stuff about quantum. I'm looking forward to this talk as well, so without further ado, here we go, Tess Schrodinger.
Can you hear me now? Oh. Alrighty, so I wanted to start by kind of giving you a background of where this talk came from. I'm not an expert. I am not a physicist. This started, as he mentioned, I've only been in IT security for about 3 years, and one of my work cohorts can attest to the fact that about 5 years ago, the most technical thing I could do was put my out-of-office email on. That was pretty impressive for me. I was getting my master's degree in security management, and I was very cleverly avoiding all the IT cyber classes because that was hard, and I couldn't do that, and I just avoided it at all costs. And when it came time to do my big capstone, and the big thesis stuff, the way my school worked was you were sat down in a room, 8 hours, you had to write 4 papers. Not 4 essays, 4 papers. And the catch was you didn't know what the 4 papers were going to be on until you sat down. So when I met with my advisor the first time, I kind of assumed that they would look at the classes I took, because my focus was counterintelligence, and they would pull my 4 questions from the classes I took. Seems reasonable. Yeah, no. They told me that if they were going to give me a master's degree, I'd better be a master. So if there's anything I didn't study, I had best study it and be ready. Which resulted in a panicked run down the hall to the man I now call my mentor. And I flung his door open and said, "Oh my God, you have to teach me everything I need to know about IT security in 6 months." And the reason he's my mentor is he didn't even blink and he goes, "Not a problem." And we did it. And I'm actually really proud to say that when they grade you for your master's, they take the 4 papers and grade each one and then give you the average. And there were 2 IT questions, so I had to write 2 IT papers, and the one of them is the one I got the highest score on, so I was really proud of that. But a little while later, with all the studying I was doing, I got so interested in it, and I started, I went to UMUC and said, I'm going to get a cyber security technology master's cert, whatever, and I started reading all this stuff, and I kept running into these articles or things on the internet and saying, when quantum computing becomes viable, encryption and security as we know it has become obsolete. Just blow it all away. And I was like, why, right? So I sat down with my mentor at lunch one day, and I said, I read this really neat article, and it said all this stuff, and why? And he looked at me and he goes, I have no fucking clue. And he's the most brilliant man I know, but I've learned that day that he doesn't know everything. So I went to someone else and I said, why? And they were like, beats the shit out of me. Okay, so I went to another person and they were saying like, I have no idea. And so as hackers, what do you do when the answer's not out there and there's no one to tell you? Well, you figure it out yourself. So this talk today is basically everything I've learned and taught myself in the last couple years because there was no one out there to give me an answer. And when I went to the DEF CONs and ShmooCons and B-sides, I kept scrabbling through the schedule looking for someone talking about quantum computing or quantum cryptography, and there was nothing. So here's the first one. So I'm going to going to start the agenda. We're going to do some classical physics versus quantum physics. This is just to give you kind of a vocabulary that we can all work with as we go forward to some of the other stuff like the computers and the cryptography. And then they're actually quantum hacking now. Y'all are about 10 years late to the party, so keep that in mind. My school background, work background, as I mentioned before, I entered security in law enforcement, in forensics, criminalistics, homicide investigation. So I tell people I was forensics, ones and zeros, not the bullets and blood was my side. And back when I was on the force, you barely even ever saw a computer at someone's house. If you found one, you'd have to call some guy in Richmond and see if the dude that does IT was in the closet. Maybe he could help us. That's how long ago this was. I have my bachelor's in sociology from George Mason University. I do have the security management master's degree. I did get the cybersecurity technology from UMUC, and I did get my security plus, which again in 3 years, I thought that was pretty impressive. So some classical physics versus the quantum physics. This is where, if you haven't taken a red pill, I brought them with me. Help yourself. The reason I say that is because quantum physics gets just weird. That's basically the best way to say it. And I want you to sticky note this in your head a little because there's a lot of research being done today where they are looking at phenomena that we would call supernatural or kind of laugh off as like, yeah, that's really, that doesn't happen. And they're really finding ways that they can look at quantum mechanics to explain some of this now, possibly. And so maybe think telepathy, just sticky note that one, and I'm going to close the loop on it in a little bit. But this gets a little weird, and if you're not used to thinking this way, it could be a little bumpy for you. Newtonian physics, or what we call classical physics, is trajectory-based. Okay, that's the way I want you to think about it. So when you have a particle, right? Does anyone want a particle? There's a trajectory to that particle when I throw that ball. And if you know the position x at any given time t, and you know the forces acting on it, gravity, wind shear from the air conditioner, you can find x as a position of t pretty much anywhere along that trajectory. You can go back into the past and say where the particle was. You can go forward into the future, and predict where the particle will be, okay? But you can always know all this pretty accurately. This model of an atom that we all had in our elementary school books, I haven't seen today's kids' I haven't seen their books to know if they're still using this model. I'd be curious to know. But this is actually about 70 years out of date, okay? Physicists sat down one day and they took classical physics and they applied it to this model of the atom, and they determined that the entire thing would collapse in upon itself within about a fraction of a second. Okay, so we have a problem now, because obviously that doesn't happen because we're all sitting here listening to me talk right now. Does this mean that classical physics is wrong, or that it's bad, or that it's not useful? No. Classical physics is really adequate to describe most of what we see during the day, to calculate these things, okay? It's fine. When we approach the speed of light, general relativity is going to kick in, and when we get down to the infinitesimally small, the subatomic level, that's when quantum mechanics needs to take over, because additional maths are going to be needed to explain why the atom doesn't collapse and things like that. So, quantum physics. I brought my happy particles with me today. Particles have mass, and we usually in our world as we sit see things as one of two phenomena. We see them as a particle, something that has mass, okay? Or we see it as a wave. That would be something that doesn't have mass. Think of water ripples on a lake or waves in the ocean. These things don't really have mass. When you get to the subatomic level, that line dividing a particle from you know, like a sound wave, that gets really blurry, okay? And there's no longer this fine distinction between the two things, okay? So at that subatomic level, things like electrons can actually have the behaviors of and the characteristics of waves, and waves can have the behaviors of and characteristics of particles. This is the more contemporary model of what an atom is. You'll see that you have the neutron, or the neutron and the proton, your electron, but making up the neutron and the proton are smaller particles called quarks. Okay, the electron is still considered an elementary particle because it does not have, as far as we know or have found, a substructure or other components. But both the neutron and the proton are composed of smaller particles that we call quarks. And these are so cute. I'm going to have to buy these. I found them last night. I was looking for a picture of quarks for you guys. So the quarks come in 6 flavors: top, bottom, up, down, charmed, and strange. And every time I say that, it makes me think of a BDSM breakfast cereal. The up and down, and it's so cute how they label these. The up and down they have the lowest mass, they're the most stable, and they're the most commonly found in our environment. That's why they compose those. The top, bottom, charmed, and strange are more exotic particles, and you're going to find these in like high energy collisions, cosmic rays, particle accelerator type environments. So a little more getting into like why we slid into the quantum physics world. There were 4 key experiments they consider like that kind of contributed to the downfall of classical physics. And when you hear the dates on these, it's actually fairly fascinating because this is not something recent. This is actually over 100 years old. First one's Planck's UV catastrophe. This is such a neat piece of trivia. You may already know this, but I didn't. I thought it was cool. Catastrophe doesn't always mean a disaster. Abrupt changes in direction are sometimes called catastrophic points in math. So there's an entire field that deals with these sudden changes in direction, and it's called catastrophe theory. I thought that was kind of cool. So Max Planck is this German physicist, and he's actually the one that originated quantum theory, and that won him the Nobel Prize in 1918, okay? And the gist of his catastrophe was that if you know, like when you heat something up, it goes from like yellow to red to white. As it gets hotter, it emits more wavelengths, and you see more light coming off of it. And then the reverse is true as it cools down. And scientists wanted to see if they could predict this curve on a graph. And so they set about to do that, and it worked really great until then suddenly it didn't work. And that abrupt point on the model where it all fell apart, they call the UV catastrophe. It's just where the model no longer worked using classical physics equations. This provoked him to come up with the equations that stated that light doesn't only act as a wave, but it comes in discrete packets, which we call photons. So that was one of the first experiments that kind of knocked a big hole in classical physics. Einstein used this photon explanation and equations. He used this to explain the photoelectric effect. Another interesting trivia point, a lot of people think Einstein won the Nobel Prize for his E equals mc squared relativity theory. He actually won the Nobel Prize for the photoelectric effect solution. And those who don't know what the photoelectric effect is, it's essentially when you shine light on metal, it causes a current to flow through the atoms because they excite the electrons in the metal. But he used this photon thought from Planck to move that through. De Broglie's discovery of the wave-like behavior of particles, he put forth in 1924 in his PhD thesis that this was about electrons, and he basically put forth that all matter had wave properties and all waves had properties of matter. And 2 years later, there were 2 scientists, Davison and Germer, and they were actually able to experimentally confirm this hypothesis of de Broglie. So they confirmed this was absolutely true. This was that double slit experiment. Is everyone familiar with that one? And then, of course, we have my favorite, Heisenberg's uncertainty principle. Actually, if anyone doesn't know what it looks like, if you find me later, I have it inked on my arm. So This is essentially saying that anytime we observe or measure a system or an object, we affect it. And so if we know a particle's position, we cannot know its velocity. And if we know a particle's velocity, we can't know exactly where it is at any given time. So, a couple concepts, because these kind of come into play later. Entanglement. This is when you have two particles that interact somehow and then split apart, and they become connected, maybe is a good way to say it. And they've observed that if you measure the properties of one particle, thus you collapse it and cause it to hold a specific state, then its partner, no matter how far away it is, will instantaneously, flip and be the opposite. And the key word here is instantaneously, because it's maybe not impressive if it happens in the same room, but we're talking like across continents, in space. I mean, they used to say when I was a kid, nothing's faster than the speed of light. Well, this is. And Albert Einstein really had a huge problem with this because of the whole breaking the speed of light thing, and he actually referred to it as spooky action at a distance. Okay? But let's close the loop now on the red pill and the blue pill. So if you think about telepathy, think about maybe someone you know, maybe a spouse or like a sibling. Maybe you've had one of those times where you guys were completely separated, either across a building or maybe, in different states, and you had one thought and maybe they had it at the exact same time, or you started thinking something and they finished it, or, I've had it happen to me, I'll be honest. But you kind of blow it off like, oh, coincidence. But there's people looking into it now, like, could this be some form of entanglement from people that have some sort of connection? I don't know, put that in the back of your head to think about at 1 o'clock in the morning when you're staring at the ceiling. That's what I do. So, classical computers versus quantum computers. This is where it gets fun. So, everyone familiar with the Turing machine? Right? Nods. Okay, this is important if you're like a journalist or someone who's not IT in here who's just curious. The Turing machine was a hypothetical representation created by Alan Turing, and it shows how a computer's supposed to work. It basically reads through a tape of bits and does one at a time. This is the picture on Wikipedia of a qubit, so we all know it's right. It's artist representation. And what a qubit is it's a unit of quantum information, and it's analogous to the classical bit. So it's just Q bit. And this introduces another concept that's really interesting and important in the cryptography, and that is superposition. So now we go to Schrodinger's cat. This is why I'm not sure if I have a cat or not right now. The principle of superposition claims that if we don't observe an object or we're not measuring it, we can't really know what state it's in. So it can kind of exist in all states at the same time, okay? It's not until we check it and measure it that we collapse the wave function and it takes one state or the other. So in 1935, Ernst Schrodinger, a very famous physicist, proposed this thought experiment. He did not do this with a real cat. Please don't call PETA. The man's dead anyway. You take a cat, you put it in a steel chamber. In the chamber is a radioactive substance, along with a device that holds a vial of hydrocyanic acid. If even a single atom decays during the test, then an alarm trips, the hammer breaks the vial, the poison's released, the cat dies. And his explanation for you to kind of put superposition in your head was, if you leave the box closed and you don't observe the cat exists both dead and alive at the same time. It's not until you open the box and look that the cat either is alive or dead. And that's kind of superposition. And without going into a ridiculous amount of explanation and mathematics, we have absolutely confirmed that superposition exists at the subatomic level. So this is not in question. So this is another picture of a qubit, and this kind of shows how a qubit exists in a state of superposition. So whereas a classical bit can be 1 or 0, a qubit can be 1 and 0 at the same time. This takes us to parallelism, which in classical computers, parallel computing is basically you have several processors linked together, and one's performing one computation, one's performing another. They're all kind of doing it parallel. But in quantum computing, parallelism refers to a single processor can process all of this data simultaneously. Because everything exists in a state of superposition, like when you looked at the Turing machine ticker tape, it doesn't have to wait for the 1 and then the 0. It can be like both at the same time, and it can go much, much faster. And the raw computing power is just, you know, this is what is the big thing where it comes to the cryptography. This was just funny. So the timeline, just a quick timeline so you can kind of see where we are in the grand scheme of things. In 1980, there was a Russian mathematician named Yuri Manin, and he's the one who was the first to propose the idea of quantum computing. In 81, Richard Feynman, he proposed the basic model for the quantum computer. And then the very next year, Paul Benoff actually put forth a recognizable theoretical framework for that quantum computer. In, let's see, 85, David Deutsch with University of Oxford kind of put forth the first kind of rendition of what a quantum Turing machine would look like. And then Arthur Eckert in 91 invented entanglement-based secure communication. In 03, DARPA's quantum network went live, and it was fully operational in October of that year. In 05, the first quantum byte, or qbyte as they called it, was announced to have been created by scientists at the University of Innsbruck. And then in 07 and 08, has anyone heard of D-Wave Systems? So D-Wave Systems is this private company that's into the quantum computing thing. I know nothing about them because they're so I think they've got better security than NSA. They are, like, depending on who you talk to, they're brilliant. They've created, like, quantum computing. You better watch out. And then there's other people like, there's no way. They are full of shit. They are lying. They cannot have what they claim to have. And it's, you know, it just depends on who you talk to. But in 07, they claimed to have a working 28-bit quantum computer. And then in 08, they claimed to have a 128-bit chip. In 09, they partnered with Google because Google wanted to use quantum technology to do image searching. So they're actually already partnered up with Google. It's a big shocker there. 2013, we had coherent superposition of 3 billion qubits for 39 minutes. This is the big one, at room temperature, okay? And the previous record for that was 2 seconds. In 2014, last year, we had scientists transfer data by quantum teleportation over a distance of 10 feet with 0% error rate, and they claim this is a vital first step towards the quantum internet. That should blow your mind. And then 2015, last week. Okay, last week, Ars Technica had an article on, they created a quantum memory that's stable for 6 hours, right? But this is at a temperature very close to absolute zero in a very, very strong magnetic field. So you're not going to be carrying it in your back pocket anytime soon. So now we get to quantum key cryptography. And I promised my work buddy I'd do a shout out to him because Wednesday of this week, when I was going over everything, I suddenly didn't understand any of it. And I actually had to re-explain all of this to myself on Wednesday. So hopefully I'll nail this. So the big concern with quantum computers and current cryptographic methods is that in 1994, AT&T, a gentleman named Peter Shor, discovered a really important algorithm that allows quantum computers to factor very large integers quickly. And this algorithm can theoretically break many of the crypto systems in use today. The numbers I read were it can factor a 1,000-digit number in about 20 minutes, which would take a classical computer supposedly 10 million billion years to do. So that's kind of, bam, why people are starting to get a little nervous. Now, in a nutshell, quantum cryptography uses physics instead of math to encrypt your data. So the key is generated using photons, and therefore you can't crack it using math. Okay, so it's very different from the cryptography we use right now. So how do we do this? So we all know Alice and Bob, right? So we have polarized versus unpolarized photons. So for those who don't know, unpolarized light waves can oscillate in kind of any orientation. Polarized light waves, the vibrations occur on a single plane. So how do you polarize a photon? You emit it using an LED, and it's unpolarized, and then you pass it through a polarization filter, which will give it a specific spin, okay? So, Alice creates a string of random polarized photons, okay? And she sends them to Bob. Bob has no clue what filter she's using. So he just picks some and throws them out there. Now, where this gets interesting is if you create, I'm going to make sure I do my arms right so this looks right. So if you create a photon that's like vertical, okay, because you've passed it through that vertical filter. If you have another vertical filter on the other end, on Bob's end, the photon sails right through. You're good. However, if Bob's got the wrong filter on the other end, say a diagonal one, that vertical one is either going to not go through at all, so you're going to get a null result. Or when it comes through, this filter is going to change its polarization, so it's going to come through as diagonal, okay? Is everyone with me so far? This like took me an hour on Wednesday to get on the whiteboard. Okay. Y'all are smarter than me. Yes. There we go. So what happens is now Alice can pick up the phone and call Bob and tell him what filter she used. She doesn't say what she sent, just what filter she used. And then Bob on the other end will compare it with what readout he got, so he knows which ones he got right and which ones he didn't, and the union of their two sets becomes your key. We good? Please say yes. Okay. So what about Eve? Well, no, that's the phone conversation. She wanted to know, you want to say it again? So basically she's like, how does Bob know? Does he transmit back to Alice? No, what happens is when he reads through on the other end, Alice will say, you know, I sent diagonal, diagonal, vertical, diagonal, diagonal. Well, Bob knows what filters he put into place. So Bob knows that 1, 2, and 4, he used the right filters with Eve. Or I'm sorry, with Alice. He knows he used the right filters there, right? So now he knows his key is 1, 2, and 4. And that's how they exchange the key. Where it comes into, like with Eve, you can't do a man-in-the-middle attack with this because of the Heisenberg uncertainty principle. So if Eve tries to put filters on this as it comes through on its way to Bob, she's going to disrupt it. And she's going to kind of skew it enough that when Bob and Alice talk, they're going to know someone's trying to measure this and they're skewing stuff up. And they can abort that attempt to exchange a key and try it again later. A couple other ones with the known attacks on this. There's a denial of service attack. They said basically you need a fiber optic line to do this, so you can just cut the line. But if you're trying to be more surreptitious and just get access to the information versus stopping it from occurring, they were discussing that you would want to go after the random number generator that determines the randomness of the polarization. So you don't actually attack the equipment and what's coming out of it, you go after the random number generator using that kind of attack so that you can affect how it creates it. So this takes us into the quantum hacking. So this is 10 years ago. Okay, so again, we're all a little late to the party here. I don't know how to say his first name, but one of the guys at Max Planck Institute in Germany, his last name is Jain, J-A-I-N. He determined that if Eve shines a light into Alice's equipment, Eve can bounce off her stuff and measure the polarization of the reflected photons. Therefore, Eve can have the polarization, which can, because she's not affecting the transmission between Alice and Bob, they will agree on a key, and then she'll be able to read anything Alice sends because she has the polarization on it. So they figured, well, how do we get around that? Well, they found this thing called an isolator, which they put up. And what an isolator does is it prevents the light from shining into Alice's equipment. And the good thing is that they were thinking like hackers. They tested it at 1550 nanometers, which I guess is the standard kind of telecommunications transmission range, and it worked great. But then they said, let's try a couple others just for, just to check this. And they found that at like 13 to 1400 nanometers, isolator didn't work at all. She went straight through and she could still get the information just by dropping her laser to a different range. So then they said, well, in addition to an isolator, they can put a monitoring device on Alice's equipment that can actually monitor if someone's trying to shine into her equipment. And they said if you combine the use of the isolator and the monitoring device, it's going to be darn near at this time impossible for Eve to get around both of those caveats. So this takes us into lattice cryptography. I honestly did not have any clue what this was. I just heard it for the first time last week. And so another huge thank you. There's a professor from the University of Tel Aviv that did a 2-hour lecture on lattice cryptography that I listened to on YouTube. So, for you guys, I did this. I actually, where is he? Spiky. I'm like DMing him like, oh my God, do you know what this stuff is? And nobody knew what it was, so I had to go figure it out on my own again. So it's actually fairly interesting. A lattice is a set of points in n-dimension space. So keep in mind, this isn't 1 or 2 dimensions. This could be 200 dimensions, okay? And why is this important for crypto? So this is important because there's several different types of lattice problems. There's a shortest vector problem, shortest independent, closest vector. There's all these different problems in the lattice math arena, and they're really hard to figure out. And we do not have, mathematically, we don't have any really efficient ways to solve these problems. Therefore, we have no efficient algorithms to program computers with to solve them. This was something else I learned about, the NP scale of computational hardness thing. This is actually kind of interesting. So lattice math falls in N, which means NP basically means it's quickly checkable, but it's not necessarily quickly solvable. And so that's why they say the lattice cryptography is going to be really good right now with classical computers that aren't quantum, just because it's so difficult and there's really no good algorithms for it. But it's also going to be really good at this time today against quantum computers because, again, there's no efficient algorithm. So a quantum computer, while it can factor an integer super fast, it's kind of on even footing with a classical computer when it comes to breaking the lattice cryptography. It's really got no advantage over a classical computer. So if you're not into lattice cryptography and you're into all this secure, you might want to start, educating yourself on this, because I'm going to definitely be looking into it more myself. It's basically right now, today, considered one of the best alternatives for post-quantum cryptographic systems. So to wrap up, because you have to have a proper conclusion according to my English teacher. So the big implications with quantum computing are going to be its effect on secure communications and current cryptographic standards. From everything I read, basically they said anything that's RSA based is toast. Once these come online, if they haven't already in the black world, you're toast if you're using any sort of factorization type related cryptography. And I think the number I saw was like around 93% uses that now, so that should make you a little nervous. The good news, if it's true, is the technology needed to build the quantum computer is really currently in a pretty early stage. It's kind of in the baby stage right now. The big challenges are keeping that coherent superposition with all your qubits. You have to have that superposition to have that parallelism and the fast processing. And right now, you know, obviously as soon as we measure it, we've collapsed that and we no longer have it. So they're still working around all this. I did read an interesting paper that talked about doing the quantum processing in a cloud and then shooting it back out, and you kind of collapse it on your end, so it doesn't affect where it's being processed. But that was about all I could understand from the paper. It was pretty high level. The big challenges in addition to that are currently you need pretty significant magnetic fields and pretty severe drops in temperature. That's why the one at room temperature was such a big deal, was because, you know, typically this stuff has to be pretty cold to work right. And then the field of lattice cryptography is going to offer a really great potential solution, but that's really only until they find an algorithm, right? And once they find that, oh goodness gracious, who knows what's going to happen after that? To which I like to say, my buddy, I was giving him this kind of thing to practice and to make sure it made sense to people because he's not technical at all. And he said, you know, this all really reminds me of the fire swamp. I'm like, what? And he said, yeah, remember when Buttercup says, you know, but we'll never survive? And Wesley says, you're only saying that because no one's ever survived. Well, that's kind of where we're at right now. It's, you know, they were saying many years ago that quantum cryptography, that's it. Be all end all. You are totally secure. You can't crack it. And we've already shown 10 years ago they've cracked it. You know, you just have to know what to do, and you've got to be that clever guy, or girl. This room's full of those people that I qualify everything I say about this with today because I know you guys and you are brilliant and you're probably going to plow right through this once you get up to speed on it. So anyway, that's my talk. I hope you found it interesting and maybe learned one or two new things and have questions. Particles? Question from the internet? Good golly. Practical quantum computing what? Well, that's... How fast would it do it? Well, pretty practical considering it'll be able to do it pretty fast. I mean... Oh. So how practical is quantum computing for breaking AES? And that's advanced encryption standard, right? Which is based on factorization, is that correct? No. What is it based on? I don't know. Remember, 3 years. Okay. Can someone else answer that question after they listen to what I just said? No, I honestly don't know, but I will.
We have someone over here.
Where?
Hi, if I may answer. So AES is minimally affected. It will reduce the effective key size to half. So at the moment, if you have AES 128, it's going to have security like a 64-bit thing. So if you're concerned about it, you might want to double the key size.
Thank you. I didn't know. Anyone else have a question that I can answer or defer to the crowd?
Coming over here.
So if you have two entangled parties, is there any way that a third party could duplicate or intercept that? So could you effectively, instead of doing key exchange, give somebody an entangled particle and then that is their reference point for doing the decryption?
I have heard of that happening. I'm going to say yes. However, I honestly cannot give you math. But there are papers I have read on that concept. They are working on that. So they are looking at that absolutely. Because that way they can avoid having the transmission using the light, if that makes sense. So yes. Ooh, got one. Next.
Yes, but just a quick suggestion for you and for myself, and there is a talk at 3 by Daniel J. Bernstein. He has done pioneer work on quantum cryptography. You may want to come to the talk and talk to him, to educate.
When is that?
3 o'clock today.
Today?
Yeah.
Awesome. I will absolutely be there.
And for the crowd, to know more about crypto, and he has done a lot of stuff on quantum.
I had marked his, and I was hoping maybe he would talk about it. So
Yeah,
excellent.
yeah.
I will be there.
Yeah. Thank you.
Anyone else? It's 3 o'clock today. It's on cryptography. I'd have
There's
to
a
pull my
talk at 3
program up.
o'clock. It's over in the Build It section. It's called SALT, a new crypto library.
Yeah.
Alrighty
Anyone
then.
else want a particle?
There's particles available up here.
Here, let me get rid of my particle. Oh my lord, I'm a